In some cases it can be faster to manually subdivide a mesh than to use Houdini's built-in tools, and by manually subdividing I mean manually writing something in Vex that subdivides a given mesh. So let's look at this rather simple algorithm that we're going to build today. Our goal here is to take this rectangle and subdivide it either horizontally or, in this case, vertically, like so, with us being able to choose where along this axis the rectangle will be subdivided into two smaller rectangles. And to keep it simple, let's keep it limited to a 2D plane, in our case the X and Z plane. So to subdivide this rectangle, what we'll first do is get the minimum and maximum positions of this rectangle, the extreme positions. This is the minimum and this is the maximum position. Next we will randomly select one point along the connecting line between the minimum and the maximum position, and this will define where the split will happen. Because what we're going to do is we will use this point's position to derive, in our case, the new x coordinate for our 2 points that we need to create. So we're going to end up with those 6 coordinates for the points, and all we have to do now is draw one rectangle with these points and one rectangle with these points and delete the old big rectangle. And we can also do the same thing, just horizontally. In this case, we're going to use the new point's z-coordinate instead of its x-coordinate to generate those new points. So in Houdini, I'm going to drop down a grid first, dive in there, let's zoom out a bit, and decrease the rows and columns numbers to 2 by 2, so we have only one single square here. Next, I'm going to drop down a prim wrangle here. So we want to work on individual polygons, that is primitives here. And currently we have only this single primitive. And the very first thing I'm going to create in this primitive wrangle here is an attribute that stores a seed value. Because later we're going to randomly choose our new point position. And for that we need a seed. So let's create a float, call it seed. And drop down a float slider, which we'll also call seed. And create it here like that. Just gonna put some value into there now. Next, I want to find out which points belong to this primitive here. And I'll do that with the primPoints function. So again, let's create an array, call it npts, square brackets, and it should be equal to the return values of my function called primPoints, which will return a list of the points in this given primitives, and it needs a geostream number, 0 in our case, and our currently active primitive number at primnum. Let's highlight this. No errors so far. Next, we need to find the minimum and maximum values in the points position. And luckily Houdini has a function for that. It's called get bbox_max and min. And these will return the minimum and maximum values of the bounding box of our current primitive. That means a cube encapsulating the whole primitive here. So let's hit F1. And we can see we can call this function either with one argument, just the geometry stream, or with the geometry stream and a group. So we can select certain primitives out of our whole geometry. And that's what we want to do. Because now we only have one primitive, so we could select the whole stream. However, we're going to subdivide this over and over again. So in later stages, we only want to select a single primitive and not the whole stream. So the way we're going to do that is by calling our bounding box min and max functions with a group that selects only the primitive that we're currently working on. We need a string that always contains our primitive number, and we're going to create that string with a function called i2a. So let's call it string grp for group equals to i2a of our primnum. Let's just look up what i2a does. It converts an integer to a string. So we will take our currently active's primitive number and just convert it into a string value, which we can then feed into our grouping field. It would be the same as just writing some number up here. Okay, back to our code here. Let's create a vector called bbmin, and it should be equal to the bounding box minimum of our 0 geometry stream and of our group, like so. And let's do the same thing for the maximum. Just copy this, paste it here, and the function is called bbmax. Next, I want to determine the direction of the split that we're going to do. So is it going to be a horizontal or a vertical cut? And the way I want to find out is by looking at the dimensions of my currently active primitive and find out if it's stretched along the x or z axis, so if it's wider along one axis. And for this, we're just going to create a third vector called bbsize, which will contain the bounding box size, which is kind of the diagonal between the minimum and the maximum. So I could also just subtract the bounding box minimum value from the bounding box maximum value, but also there's a function for that, so why not use it? Get bounding box size, and again it's called in the same way as our get bounding box minimum and maximum, like this. And now we want to look up if our bounding box size x-axis is bigger than our bounding box size z-axis. And if it is so, let's set an integer attribute which we'll have to specify beforehand. Let's call it cut dir for cut direction. So if my x-axis is bigger than the z-axis, let's set our cut direction to 0. Or else, if the z-axis is bigger than the x-axis, set our cut direction to 1. So this is just a kind of a boolean which can be either 0 or 1 and determines if we're going to cut horizontally or vertically. So in this case when it's 0, so when this axis is bigger than this axis, what we want to do is we want to make a vertical cut, and if the cut direction equals to 1, we want to make a horizontal cut. Next, let's randomly generate a position on this vector connecting the minimum and the maximum. So let's create a float for that, call it cutPos, and it should be a random value. Let's use our current prim number plus our seed. And now let's get to the meaty part and actually build the subdivision. So let's comment this here and call it subdivision. The first thing we want to do is create this new point position along this diagonal line. So let's call it vector cut. And what we want to do is we want to interpolate between the minimum and maximum value of our bounding box. And there's this function called lerp, which is short for linear interpolation. And lerp takes 3 arguments. The first value, bounding box minimum, the second value, bounding box maximum, and what's called a bias, which is a value between 0 and 1, which will determine if the resulting value will be closer to our minimum value or to our maximum value. And what we want to do here is use our cut position, which is between 0 and 1, as a bias. So this will spit out a position that lies on this diagonal between minimum and maximum, and is determined by the value of our cut position, which should be between 0 and 1. Next, we're going to create 2 variables, which we'll need for the creation of our points. A vector with the point position, which we'll not initialize yet, and also an integer called new pt, which is going to store the new point number, which we'll also not initialize yet. So let's check if our cut direction is equal to 0, and if it is so, let's do something. Let's create our first new primitive. Call it new prim, and let's use the addPrim function to add a new primitive. Again, let's have a look at this function. And there are several versions how I could call this. On the one hand, which I'm going to do here, is I can just specify a geostream and the type. And when you scroll down here, these are the types that we can create. And in our case, we want to create a closed polygon with the keyword poly here. And I could also immediately add point numbers. So this new primitive automatically gets created with its vertices already. However, what I'm going to do is I'll first create the primitive and then add these individual vertices. That means the corner points successively. So let's just create the new prim. Again, 0 geostream, and it should be of type poly for polygon. So let's create some new points and add them as vertices to this newly created primitive. Let's start with our first point. Let's use our vector called pos, and for the first point it should be equal to our minimum bounding value. Next, let's add a point. So we're just going to use the new pt variable that we already created up here, and it should be equal to our addPoint function's return value. Let's have a look at addPoint. 2 ways of calling this. We're going to use this one here with our geostream 0 and our newly created position vector. So 0, pos. And finally, let's add this newly created point as a vertex to our newly created primitive by calling the addVertex function. Again, let's have a look at this. It takes 3 arguments. The geostreams handle 0, the prim number to which we want to add this vertex, and the point number, which should serve as vertex. So 0, new prim, new pt. And we added a first vertex there. Let's copy this block because we're gonna do it 3 more times. So the next position is a combination. So this was the first point that we specified. Now let's specify this one, which in our case has our cut x value and our minimum z value. So let's set our new vector to our cut.x component, to our minimum y component, which doesn't matter in this case because we're working on a 2-dimensional plane, so we could also set it manually to 0, but in this case let's just stick with that, and our minimum z value. And of course this should read bbmin, because that's what we called it up here. Next is this point here, so let's again copy this block here, paste it down here, and the only thing we want to change is now we have the bounding box maximum z value. And the final point is this here, so let's create this as well. Again, copy this 3rd time, paste it, and in our case this should be the bounding box minimum x. So when we highlight the primitive display now, nothing happens. And I suspect that is because our cut direction is not set to 0 in this case. So let's just take care of that. And just for debugging purpose, let's just set our cut direction to 0 now. And we can see we just created another primitive. However, this is overlapping our original primitive quite a bit. So what we'll do is we will delete the original primitive and also create the second rectangle that's needed for subdivision. So let's create the second rectangle now. Maybe comment this out and say first quad. And let's copy this whole block here and paste it down here. Call it second quad. And the missing quad will be this here. So let's start off at this point, then add this, and finally this point to complete the quad. Okay, let's start with this here. So we're gonna create a new vector for the first point of the second quad using our cuts x position and our bb-min y and bb-min z position. That's starting to look funny. So let's quickly add the other points. This one here, and finally this one here. Which totally doesn't look right, so let me quickly check what went wrong here. And yeah, it would be a good idea to create a new primitive for that and not write all of these 8 points into the same primitive. So let's just copy this line here and paste it down here. So we now have these 2 quads created. And also for better readability of our code, let's just cut this here and add it below our first quad, like so. And the only thing that's left to do now is we have to delete our original primitive, which is done with the command remove prim. Let's look it up. It takes 3 arguments, our geostream, primitive number, and an integer, which is 0 if we don't want to remove the points attached to this primitive, and 1 if we also want to remove the primitive's points. So we want to remove the original primitive as its whole, so including its points, 0 geometry stream, current primitive number, and then including the points. So we now have only 2 primitives left that we newly created. And when dialing in that seed value here, we can see the position at which we're splitting jumps around. And what I'd like to prevent are those positions that are very close to the edge of a certain quad, because that will mess up the look, because it'll get very dense very quickly. So to do that, let's skip to the part of the code where we generate the random position here, and let's use another function called fit01, which will fit a value between 0 and 1 to those values that I specify here. So the minimum value should be 0.1 and the maximum value should be 0.9 in my case. And we can see now we don't get as close to the corners here. Okay, now we specified the vertical cuts. Let's do the same for the horizontal cuts by just copying all of this here. And we checked if our cut direction is 0, and if it is not 0, let's drop down an else statement and then paste our code here. And just to make sure that we can see the correct part of the code, let's set our cut direction for this case to 1. So we will always execute this else block here. And what we want to do now is we want to first draw this quad here by going this point first, then this point, then this, and finally this here. So the first point position is already set, and that's correct. Then let's go to the minimum x position and our cut z position. Then to our max x and cut z position, and then finally to our max x and minimum z position. And of course this is bb max. And now we can see we just created this rectangle here. Let's set up the point order for the second quad here as well. So let's do this point first, then this, and finally this. So first is minimum x position, cut z position, minimum x position, cut z position, then min x, max z, then our maximum point, and finally max x and cut z. Fingers crossed, and we created our second quad here. So that's been a lot of code, and it kind of messes up this whole Vex snippet here. So what you can do is in the editor, press Alt and E, and open up an external editor, which you can resize and get a bit more space to get an overview of the code. And we can see all this manual creation of quads here is kind of tedious. And wouldn't it be nice to have a function which does exactly that, what we coded here? And luckily, Vex lets us define user-defined functions. That means custom functions, where we can encapsulate all this code to be just called with a single line. So when you go to the Vex section of Houdini's help, you can see this section here called Vex language reference. And within the language reference, you find this subsection here called user-defined functions. And what this is about is it lets us specify our own functions. So for example, when we're calling nearPoint or nearPoints, that's a function that side effects already implemented for us. However, we can also implement our own functions using Vex. And that's exactly what we're going to do for the subdivision algorithm here. What we need in order for that is this syntax here. So I like to specify a function starting with a function keyword. It's not necessary that you do that. However, it's safer. In some instances, your functions won't work, especially when working with array functions. Then we're going to specify the return type. So if our function returns something, if our function returns a value, which in our case it does not. So the return type here is void. So it's just a function that does something and does not return anything. Then the name of the function, and finally the arguments that this function takes. And then within the curly brackets, the code that our function will execute. So let's try and build our own subdivision function. What I'll do before my whole program starts is I will add a comment, call this one main. This is the main body of my program, and up here we'll specify the functions. And the first function we're going to specify, let's call it function. We said it won't return anything, so it's void. And let's call it subdiv for a subdivision. This function will need some arguments. And the arguments we'll need is our minimum and maximum position. So a vector, call it bbmin and bbmax. It'll also need a float specifying where between the min and max position our cut will happen. And it'll need an integer to specify if the cut will happen horizontally or vertically. Like that. Let's hit apply and accept. And we can see no error messages yet. So what I want to do now is take this whole block here where we subdivide and create our new quads. Let's cut that and paste it up here. And also let's indent it. And we immediately get lots of error messages. That is because we omitted two things that we need, which are those here. So let's cut them out as well and paste them on the top of our function. Let's get the indentation right, like so, and we don't need that comment anymore because it's clear it's in the subdivision function. Better, no errors yet. However, also my subdivision has gone because now we're not executing this function that we specified up here. So let's move down to our main code here. And down here where the subdivision was originally happening with all that code, let's just call our function, call it subdiv. And it needs our bounding box minimum, our bounding box maximum. It needs our cutting position and our cutting direction. Like so. You can see now we have this subdivision back, and we can also manually change parameters here. So let's, for example, let's not use this cutting direction, which is currently set to 1, but instead manually set this parameter to 0. We can see now that works perfectly. And also let's test with the cut position. 0.5 should split it right in the middle. Yes, that is working. Okay, also get rid of this manually set cut direction, and we're back to our originally working code here. And although this function took quite a bit of space here to define, what it allows us now is just with one line of code call all of this code that's within the function, and it's been neatly packaged away for us not to bother with. And what we can do now is wrap this thing into a for loop. So this will run the primitive wrangle over and over again while merging the resulting geometry. So we will keep on subdividing those newly created primitives now. When we set it up like this, it goes in here, that goes in there, like so. Let's highlight this here. And now by driving the iteration number, I can specify how finely my grid gets subdivided here. However, what I'd like to do is for each of those iterations, I would like to change my seed. So my subdivider is not always subdividing at the exact same seed. In order to do that, I'm just gonna go on my repeat begin node here, create a metadata import node. And when you middle mouse on that node, you can see it's got those detail attributes, storing, for example, the iteration count, the value of I, that's the value of our counting variable, the number of iterations, and so on. So in our primitive wrangle, down here in the seed, let's drop an expression and let's access the detail attribute of our node called repeat begin metadata, and we want to access the iteration, and we always want to access the 0 component, like so. We can now see we've got this iteration number piped in as a seed here. So that is our manual subdivider. Should be noted that it also should work on non-square grids, so let's try that. Perfect. And also it should work on grids containing more than one quad. Works too. Neat. Let's dial up the iterations a bit. And next what I want to do is use the measure to get the area of each primitive here. Then let's have a look at the normals in here. We can see some of them are the wrong way around, which I could fix in two ways. Either I would change my order in which I add the points here in the subdivision, which would be the way cleaner way to do this. However, I'm just taking the lazy approach here and just add point normals here, which of course will also be pointing in both directions. So I'll add a point wrangle, and in this case just cheaply fix it by checking if my normal's y component is smaller than 0, and if it is so, I will multiply my normal times -1, like so. Let's check that. So that worked. All those normals point in the same direction. And I'm doing this because I want to extrude this now. However, I want to extrude each quad differently depending on the area of the quad, which we already measured here. So middle mouse on this, we can see we have a prim attribute called area. However, I want to remap this, because when I drop this into the poly extrude here, and let's dial back our iterations here to make the geometry a bit more lightweight. So when I pipe this in directly into the poly extrude, I can set the extrusion mode to use point normals, and then under local control, let's check distance scale and pipe in the area as a control attribute. So my area value now controls how far this thing gets extruded. And let's dial up the distance here. Let's not pre-compute the point normal, but use the existing one. And although this is already looking kind of neat, let's add another normal sub to cusp away those normals so that we don't get rounded appearance here. However, what I'd like to do is remap this area value a bit in order to tweak the appearance tiny bit. I'm going to do that with a primitive wrangle. And there are 1,000 ways how you could do that. You could also do this with a bop and a ramp, or with Bex and a ramp. However, what I found neat was I can set the area value to be the power of my area value to 0.5. So these big areas get flattened down a bit. And also let's add a bit of randomness to it. About 0.1. Now maybe in this case it could be more. Like so. Okay, let's dial up our iterations again. You can see now we get this city-like or microchip-like or whatever you like to call it structure. Let's increase the distance a bit. And maybe dial back on the randomness factor here. So it's now down to tweaking values. And the final thing we need to do to arrive at the intro image of this tutorial is we have to add our custom connect adjacent points. So let's first use an add sub to get rid of everything but the points by checking delete geometry key points. So we now only have these points left here. And then let's open up our old array sample file here where we built this point connector, and just take this node which does the connection, copy it and paste it in our newly created setup, and then just wire it up below the add. And now again, I could tweak those parameters of this sub here again to change the appearance of my grid-like structure that's emerging here. And that's how this intro image was created. So to sum up, the main takeaway today, I think, was that you can specify your custom functions to hide away all of this mess of code here, to be able to call it with just this single line here in your main routine, in your main part of the code. And that is really helpful when you're creating a library of functions that you can then pass on to your fellow TD or artist.